Okay, so in this lecture today, lecture 13, we will make use of the things that we've learned so far and talk about a specialized technique that exploits fluorescence imaging to obtain information about the molecular environment in which the fluorophores that we probe reside in. We have really all the tools we need to describe these processes, and we will see that using the lifetime as a readout, the fluorescence lifetime as a readout, rather than just intensity, we can gain information that is on a scale that's much smaller than the wavelength of light. So in a way you can say this is the first super resolution method, although the super resolution isn't in the image information per se, not in the way that the image is constructed. It stems from additional information that comes from the fact that the lifetime is dependent on the immediate molecular environment of the fluorophore. You shall see what that means. So I will begin the lecture by now turning to the visualizer here, and I will go through the concepts of what is called Flim, or fluorescence lifetime imaging microscopy. And so to begin with, we should just recap what the lifetime is about. So if we have a two-level system, as usual, 1 and 2, then I can drive population up at a rate B12, as we've seen in the last lecture. And the population we drive into the upper state can decay down by fluorescence at a rate A21. And it can also be quenched. So these are losses at rate Q21. I have ignored the possibility of stimulated emission, i.e. I've not drawn in here the stimulated emission process at rate B21, because for most systems that we deal with in microscopy, the population in level 1 is much higher than the population in level 2. We've said this is the case because we're dealing with electronic transitions, and so at room temperature, most of the population resides down here. Also, if we use small laser powers, then these two processes dominate over stimulated emission. So it's much more likely that the population from up here comes down this way and that way, rather than by stimulated emission. So we might drive out a B12, but we can ignore the stimulated emission part. And that is certainly true for the conditions that we need to do fluorescence lifetime imaging microscopy. So to recap, we said that the fluorescence quantum yield, theta f, is given by the rate at which the fluorescence is generated over the total loss rate, which is A21 plus Q21. And just to give you an example, in the lecture notes for this lecture, you have a structure of a fluorophore called Alexa 488, which is used a lot in biological fluorescence. And in fact, that's a dye, an organic dye containing conjugated rings that has a very high quantum yield. Its quantum yield is 0.9, which means that for every 100 molecules that you excite, 90 will actually emit a fluorescence photon. So it has a very, very high brightness, this molecule. And so again, I just state this, what I've already said. We have neglected, oh God, my spelling, neglected B21 here, which holds for low laser powers, and it holds for the case where N1 is much larger than N2. Okay, now let's assume we excite this molecule here with an excitation step function. So the way we draw this is, so I draw a time here, and I have my light is off initially, and at t equals 0 I turn it on, and then it rises rapidly in a step, and then I just leave it on. It's like switching a light switch on, and the intensity of excitation, or the irradiance, is IEX. What does the population in level N2 do? So, of course, initially the population is 0, and then it will start rising because we're pumping population up until, of course, these rates here, A21 and Q21, cause this system to reach steady state. And we already know from the last lecture what we get is this. The population, if I draw this underneath, for level N2 will be 0 initially, then the laser switches on. We first get a linear region, for a linear rise, as we've discussed, of the population, and then it will fold over to reach steady state. And we've already mentioned that the steady state population here is given by B12, rate at which things go up, times the initial population in level 1, N1 naught, which is of course the total population, divided by R. Okay, so that is the total rate that has all bits in there, B12, A21, Q21, and so on. And if I look at this initial linear region, we said for very small times, the initial growth is linear, and it grows as N1 naught times B12 times T. And so you remember, in between the whole system can be described by this formula here. So this describes this function. For very small t, this reduces to this, and then for very large t, this reduces to this green function here. Okay, so let's now turn to two pictures in which we can understand this process of fluorescence lifetime imaging microscopy. So the way we can think of it is first by considering a large number of molecules. So let's first begin by considering a population of molecules. And so in this picture now, what I'll do is I draw the same picture as before. I have T here. And now let me draw the excitation as a finite pulse. It's like a rectangle function. And I start this before t equals 0 for this discussion. And I switch the light off at t equals 0. So you have here a rectangle function for the excitation. So that's IEX. And let me just draw on top of this graph. So the y-axis here represents two different things. The intensity here is in blue, and in green I draw the population in N2. So we said if this is sufficiently short, this pulse, then the population rises linearly and so it will reach a population here, N2, which is equal to N1 naught B12T, which is equal to N2 naught. So essentially, at time t equals 0, we reach the maximum population. So it rises linearly until it reaches this maximum. And then when we switch off, well, what happens now? So we have the population is N1 naught B12T, which we just say is N2 at time point 0. And so we turn off the laser. The laser is off at t equals 0. So typically one uses a laser because one uses short pulses, and you can do that conveniently with a laser light source. And So we know then that the population up here, dN2 by dt, after t equals 0, will now decay at minus n2 0. So it's that population times the rate at which that decays, which is just A21 and Q21. There's no other loss because the laser is off, right? And in any way, we neglected it. We neglected the stimulated emission rate on this. So you can solve this equation, and that means that N2 is equal to N2 naught times e to the minus A21 plus Q21 times t, or N2 naught times e to the minus t over tau. And tau is here 1 over A21 plus Q21. So the way we've written this is we've defined tau in terms of these rates, A21 plus Q21. So tau is the inverse of these rates. Rate has units of per seconds, so the lifetime has units of seconds. And so that is what we now recognize from the previous lecture as the fluorescence lifetime. So what does this actually mean? How do we interpret this? So in this picture, if we have an initial population in the upper state of N2, what tau represents is the time for that population to decay down to 1 over e of N2 naught. Okay, so that tau, after time period tau, given by 1 over A21 plus Q21, the upper state population will have decayed to about, 36% of its value, 1 over e of its value. So just to give you a number for this, for Alexa, if I had Alexa 488, again the structure is the molecule that we had before, then the lifetime tau is equal to 4.1 nanoseconds. So this is the time at which, 66% of the molecules will have decayed of the excited state molecules. And importantly though, for Alexa 488, this happens at a solution which, so this has been measured for a solution of 50 millimolar potassium phosphate, 150 millimolar sodium chloride in aqueous solution, which gives you a pH of 7.2 at 22 degrees C. And so why am I so particular about mentioning this? Well, the reason for that is that this lifetime changes if the pH, for example, changes and if the temperature changes. And the reason for that is this Q21. This loss term is greatly affected by the molecular environment. So, for example, if I increase the temperature, perhaps this tau decreases. So you can see why this is useful already. It is useful because changing the environmental condition is reflected in lifetime changes, and these lifetime changes can therefore, if we understand the physics behind it, be used to say something about what is happening at the molecular level. Okay. So again, it's clear now to see what this means, this lifetime, in terms thinking about a population of molecules. Equally importantly, we should try and think, what does the lifetime mean when we deal with a single molecule that we may excite? So to look at this picture, we go to picture B. Both are important for us to understand fluorescence lifetime imaging microscopy. So the single molecule picture, put this in apostrophes here, we draw this as follows. let's, for a single molecule, make the excitation pulse very, very short. So if we make this very, very small rectangle, then in fact this starts to approximate a delta function at t equals 0. And what happens? So we have this very sharp pulse of light. So we call this delta Ex for this discussion here. What happens next? So a single molecule will be hit by photons from this delta function. They arrive and they hit it like, I'm hitting a bell. And what happens next? Now the molecule can be excited into the upper state. It goes from state 1 to state 2. And then what? Well, there will be a photon coming back, a spontaneous emission. So at rate A21 it will be generated. It can be quenched down, of course, as we've seen as well. So for Alexa 488, that probability is about 10%. But there's a 90% likelihood that for the excited molecule you also get a photon coming out. One photon can only come out at a particular time. So let's just do this. Let's put the pulse in, we excite the molecule, and we now wait, and perhaps after a time t1, we get a photon, the first photon coming back. I put one pulse in, I wait, and then after a delay tau1, a photon comes back. All right, I don't know exactly when it comes back, but it will be within a certain time period. Let's do that again. Let's do the same experiment again. Let's take another, put another pulse in. I put the stop clock on, and then a second pulse, a second photon might come back. Maybe this one comes back at this time here. So this arrival time is maybe tau2. Okay, and I repeat this. Maybe I could get the next pulse coming back here at 3. So this is the third time I excite the molecule. It comes back at an arrival time t3. So tau 1, 2, 3 are the photon arrival times. And the point now is that, of course, there will be a distribution, a likelihood distribution. So you will get, if you could keep doing this many, many, many times, you'll get a distribution of photon arrival times. And the expectation value, so if I call this T0, so this just to specify that this is what by this T0 I mean the instance at which the photon arrives, the photon arrival time. So the distribution, so the expectation value of the arrival time is tau. So the most likely time is in fact the fluorescence lifetime. The variance of this turns out to be tau squared. It's normally distributed. The lifetime decay can now be interpreted as a function, so let's call it f of t, is the probability density function of photon emission. So in other words, if I put lots of pulses in, I map out the arrival times, I may get a distribution. Well, I will get a distribution that looks exactly the same as in the previous picture. That distribution will be f of t, and that is the T0 or ft, as I've written down here, which is essentially the probability of photons arriving. It's very high initially, and then of course this width here will be the fluorescence lifetime. So that is the expectation value of this probability distribution. So the idea in fluorescence lifetime imaging in the time domain as we've drawn here, is essentially to put short pulses of light in. You interact with molecules. You wait until the photons come back. So you know when you put the photon in. You wait until the emission photon comes back. You measure this time. You repeat this process lots of times. And then you get a distribution. That distribution corresponds to the fluorescence lifetime. This picture is exactly equivalent to having a bunch of molecules in state N2 initially. And then just you wait until until the molecules have de-excited. And of course, the population will decrease to the 1/e of its initial value after a fluorescence lifetime tau. And that is precisely what this means. Okay, so what we do is we just put these delta function pulses in, but unfortunately, of course, you cannot generate physically, although light, you can make very short light pulses, and you can get as close as you want with delta functions. Any system that you, unless it's very, very specialized, will have a distribution. So this function, this excitation pulse, is not, of course, a perfect delta function. So in reality, the excitation function will be spread out a little bit. And so I define now what I call the instrument response function. So let's call this the instrument response. The instrument response function. And so in reality, the excitation pulse maybe it looks like this. Maybe it looks something like this. So it's not quite a delta pulse. And of course, the photon emission PDF that we've seen, or the which has this characteristic decay shape, it looks like that. So that essentially that's the delta function response that we've just plotted. So this would be this delta function response. So it looks like this, right? So that's f of t. So we have t here and t there, and so in reality, of course, the response of the molecules to this excitation pulse IEX is a convolution of this profile here with the impulse response function. And so this convolution then will yield something that may look like that. So it may then look something like that. So for very accurate measurements, you have to deconvolve this. So we call this function now f time domain of t. So the FTD, just say this is the time domain signal that I get. Putting this pulse in, then I will get this time domain signal as a function of t coming out for an excitation pulse of that shape. You know, either putting that into lots of molecules or repeating this with low intensity pulses on individual molecules one by one. I'll get this sort of arrival time distribution as a result. So just to spell this out in an equation, the time domain response is equal to the excitation shape and time convolved with the delta function response of the molecule that I'm testing. In reality, of course, the instrument response may also include things like timing jitter. So, for example, the electronics that you take to measure these time intervals are very short. You know, we already saw that a typical a typical fluorescence lifetime is 4 nanoseconds or 4 billionth of a second. And maybe you need 10 to the minus 12, 10 to the minus 10 resolution. So you need seconds resolutions. You need very small resolution. And so if you have any jitter in the electronics to measure these short speeds, then of course there's an error there, and that will be convolved into this instrument response function just the same way. And you need to know that to get the most accurate data out. So you understand the physics of it. There's not more in it in terms of what goes on, but the detail is just technology, and people know how to deal with this. You measure the instrument response on something that has a very short lifetime. So imagine if you had something that has a lifetime that is essentially just a delta function. So if this is extremely, extremely, extremely short, a very short lifetime, something that you could use is, for example, an object that scatters light. So scattered light, not fluorescence, but just scattered light, will just reflect the excitation pulse back into your system. And then actually you get a convolution with a delta function, which gives you the instrument response function itself, right? So in fact, we can call this here also the instrument response function, which would be what you get if the lifetime was infinite and this was a delta function. All right. So this is called the IRF. So yeah. Okay. With that, I want to talk you through. I would want to go now to my overhead slides and just on my computer, and so if you look at this here, I just wanted to give you a few examples first of all to say, why is this a useful thing to do? Why do we want to measure the fluorescence lifetime? And here are some examples. So what you see on the right-hand side of this image here is a picture of a microfluidic device, a small device, that can generate small droplets, and each droplets contain a few copies of DNA. You can see that if you can see this, the droplets go. I don't know whether you can see my mouse. Let me just put the laser pointer on. So you can see the droplets go in the zigzag path around around this device, and then they enter this central region here, and this region contains a heater, because what you need to do in PCRs, you need to cyclically heat the sample up and down. And so in each of those droplets you get this PCR reaction, and of course it's a fantastic tool here because you have these nano confined droplets in which you can multiply DNA, and so you can look at lots of conditions in quick succession, right? Because you have so many droplets in there at once. But the problem is, how do you know what the temperature is inside these droplets? Because that's very critical to get the PCR reaction to go right. And in fact, what Shaley et al. Did in this particular paper here in analytical chemistry, this is a research paper from 2009, they added a dye that looks like this, rhodamin B. It's a very commonly used organic dye, to each one of these droplets. So in addition to the DNA, it doesn't interact, doesn't do anything to the PCR reaction. But interestingly, this dye here responds to temperature. So the Q in the 1/A plus Q bit is highly temperature dependent, and you can see how the lifetime, the fluorescence lifetime of rhodamin changes as you increase the temperature. So it decreases as a result of temperature. So by just measuring the lifetime inside these droplets, you can get a temperature readout. It's very useful. And you can do this in the microscope. Here's another example. So this is a, sorry, I jumped 2 slides ahead, so I wanted to show you this slide first. Here is a dye which looks like this here. It's a so-called molecular rotor, so you have these conjugated rings, and they are connected with an axis. And so these two ring systems can rotate with one another, and when they rotate against each other, the lifetime of this molecule is very, very short. And if they are stable and planar, these molecules, then the lifetime is very long. And so if you put this probe into a solution with a high viscosity, the rotation is hindered, and therefore the lifetime is long. And conversely, if the rotation, if the viscosity is low, it rotates very quickly and the lifetime goes down. So you see this equation down here. It's called the Förster-Hoffmann equation, and it tells you how lifetime tau. You don't have to remember this. You would be given this if you need it for a calculation. But just you can see that there is a viscosity term in there, eta, and there's the 1 over A21, which is essentially the natural lifetime of the molecule, and you can see how as you increase the viscosity, the lifetime goes up. You can calibrate this system, and then you can use this, for example, in cells, and the dye can then report whether inside the cell you see these dots, and you see bluish regions and green regions. I don't know whether you can see it on the slide, but I hope you do. And so you can measure that there are compartments within the cell where the viscosity is very different. And that, of course, is important for molecular transport inside the cell, and tells you interesting things about what may what compartments you might look at by just looking at the fluorescence lifetime. Here is a third example, very different example. So I told you that most tissue and so on contains proteins, lipids, and so on. There is not very much contrast that you gain from intrinsic fluorescence. You usually label things because proteins and other components in tissue all have similar fluorescence spectral profiles. So this is an example here of how we can gain contrast from tissue that you don't need extrinsic labels to look at. So you look at cancer tissue here, and if you look at the fluorescence lifetime, you can see that cancerous tissue here has a shorter lifetime compared to the non-cancerous tissue. And although if you looked at spectra from these regions, you wouldn't be able to distinguish very much between the intensity from one or the other. So here's an intensity image of this tissue, and you may see there's some tumorous stuff here, but these are already fully grown tumors. But around here, it looks very homogeneous. But actually, what you see on the lifetime images is that there are blue regions in here, which already indicate that the cancer has spread out into adjacent tissue, which you wouldn't see by just looking at intensity itself. And why is so you can see here a spectrum. So this is a lifetime spectrum. So you look at the lifetime of healthy tissue in red here, and the tumor tissue has a lower lifetime. And the reason for that is that the tumor tissue is more oxygenated, and oxygen is a strong quencher for most fluorophores. And so the intrinsic fluorescence is quenched more strongly in cancerous tissue than it is in healthy tissue. And so you see this very useful diagnostic. For example, you can put an endoscopic microprobe down into the esophagus, for example, and then have a look at tissue, and the reflected light from the fluorescence lifetime tells you whether the tissue is cancerous or not. So the advantages of fluorescence lifetime imaging are, first of all, the lifetime is independent of the fluorescence intensity. And so, in fact, one interesting thing is because you're always measuring decays, you're measuring arrival times, and these are relative measurements, right? Relative to a start and an arrival position. These don't depend on what the intensities are. So if you have laser power fluctuations, that doesn't matter. All you need is good timing circuitry in the system. The lifetime is also independent of concentrations, so it doesn't matter whether the initial population N2 is very high or whether it's very low, because all you're measuring is the decay rate, and the rate of decay doesn't change with concentration. Finally, one great aspect of using fluorescence lifetime is it gives you a chance to discriminate excitation light from emission light. So in case you can't distinguish with color, which is what we relied on so far in fluorescence microscopy, you can also use time to discriminate the background, because the excitation light will be earlier than when the signal comes out. So you could just filter your detector to ignore the excitation pulse and only look when the fluorescence comes back. And finally, the fluorescence lifetime is a quantitative measurement. It's quantitative. So it's easier to interpret than, for example, the fluorescent signal itself, where you need to know a lot about the system itself to get the signal calibrated. So the lifetime itself is an absolute quantity. There are drawbacks. The measurement of fluorescence lifetime in the microscope is really expensive to do. You need some very expensive equipment. And the other is that you need quite some expertise to analyze the data. So in every pixel you need to actually look at these decay curves, deconvolve them and so on, and that requires a lot of specialized expertise. I just finish this part by quickly telling you how one measures fluorescence lifetime in a technique called time correlated single photon counting, TCSPC, time correlated single photon counting. Very simple. We've discussed all the physics already. You put a single photon in, or a very low intensity light pulse in, and you wait until a single photon comes back. From the first molecule, you measure that time. And so you just keep repeating this. So perhaps the first arrival time is 6 or 7 nanoseconds, as you can see here for this particular sample. I think this may in fact be again Alexa. And so maybe I'll record that first lifetime, and then I do this again, second photon arrives, and the next photons arrive, and I keep going, and I essentially get a histogram. And that histogram, when I bin these things together, will reflect exactly what the fluorescence lifetime decay curve is. Of course, convolved with the instrument response function. And so when you take that out, you can get actually very, very nice lifetime measurements. So TCSPC is the gold standard of fluorescence lifetime measurements. It's the only technique. There are some other variants. You can measure this also in a technique called frequency domain Flim. We are not talking about this, not as widely used. TCSPC is the gold standard for this, but it's relatively slow because you need to put lots and lots of pulses in to record the lifetime. Here you see how you measure these short arrival times. So of course it's expensive. We really, what you do is as follows. So you have a laser pulse train. So you have lots and lots of pulses coming in, and the pulses are spaced at a certain distance so that they're more widely spaced than what the decay profile is, obviously, so that not one pulse bleeds into the next. And then what you do is you excite. One laser pulse comes in, it's shown here in blue, and you measure when that's arrived using a photodetector. And you at the point when that signal here arrives electronically, then you put a stop clock on. Essentially, that's just a voltage integrator. The voltage integrator charges up a capacitor, and then once the signal photon arrives, which you measure with another detector here, you stop charging the capacitor and you read off the voltage. So what this is called is an amplitude to time converter. And so once time to amplitude converter, once that's done, the voltage is essentially plotted as part of this histogram converted to what the arrival time was. And these boards here, they cost an enormous amount of money. So you're talking tens of thousands of pounds for this timing circuitry, but it can be done now routinely. And with that, I finish this part of the lecture, and I will go into one application, which is FRET, first resonance energy transfer, to measure molecular distances with Flim. Thank you.